Hello students, in this video we'll see an example of a constant coefficient ODE that has complex roots and how we can use Euler's formula to find real solutions of the ODE. Let's consider 4y double prime minus 4y prime plus 37y equals 0. The characteristic equation of this problem is 4r squared minus 4r plus 37 equals 0. We'll solve this by completing the square. We'll pull out a 4, and then we'll have r squared minus r plus 37 over 4 equals 0. We'll cancel out that 4. And then we'll complete the square, r squared minus r. And to complete the square, recall that we take the coefficient of r over 2 and square it. And that's the factor we add. The coefficient of r is -1, so this is -1/2 squared. -1/2 squared is +1/4. So I pull a +1/4 out of 37 quarters, that leaves me with 36 over 4. And that's the same as 9. So what we have here is we have r squared minus r plus 1/4 plus 9 is equal to 0. These first three terms will always be a perfect square. They are r minus 1/2 quantity squared plus 9 is equal to 0. From this we can easily solve the equation. This tells me that r minus 1/2 squared is equal to -9. So that tells me that r minus 1/2 is plus or minus 3i. And therefore r is 1/2 plus or minus 3i. We know that the solution will therefore take the form y equals c1 e to the 1/2 plus 3i x plus c2 e to the 1/2 minus 3i x. And this is the complex form of the solution. We can also notice that we can write, by Euler's formula, e to the 1/2 plus 3i x as e to the x over 2. And then I can have a cosine of 3x plus I sine of 3x. And therefore, the real part of this is e to the x over 2 cosine of 3x. And the imaginary part is e to the x over 2 sine of 3x. And both the real and imaginary parts of the solution of this complex solution would be a solution of the original equation. So we see that both of these solve the ODE and are linearly independent. So I can find the real form of the solution by saying that y is c1 e to the x over 2 sine of 3x plus c2 e to the x over 2 cosine of 3x. And this is the real form of my solution. So, to summarize, when we have a constant coefficient ODE that has complex roots that occur in conjugates, we write out the complex form of the solution, and then we look at the real and imaginary parts of either one of the exponential terms with I in it, and the real and imaginary parts together will both be solutions that are linearly independent. So we can either write the solution in real form with exponentials and sines and cosines, or in complex forms with complex exponentials. Thank you very much.